All right, well, we'll get started here and welcome some others in as we get going. But thank you all for coming today to the SEFS seminar. I'm John Marsloff. I'm a professor of wildlife science in the school. And it's my pleasure to introduce Dr. John Withey to you all today. John is no stranger to most of us here at SEFS. He did his master's and PhD here and then came back after teaching a bit and did a postdoc as well. His bachelor's was at Pomona College, and he then did his master's and PhD in my lab working on crows and urban ecology. We had a large urban ecology program at the time John was here, and he was one of the first students going through that. Several of his early publications are about interdisciplinarity and graduate education and urban ecology. He then went on and did a postdoc in Panama with STRI, the Smithsonian Tropical Research Institute down there on birds. Took a year of sabbatical fill-in at Lewis and Clark in the biology department. Then, as I said, came back and did a postdoc for 2 years with Josh Lawler, and some of the things he'll be talking about today emanated from the work he and Josh and their collaborators did with economics and other aspects of conservation. He then took an assistant professorship at Florida International University, and then after 4 years there, went to the Evergreen State College, where I'm sure he was glad to come back to the Pacific Northwest and enjoy his home state again. But he was a member of the faculty there for the Masters of Environmental Studies program, which he's remained in, and now he's the acting director of this year. And his talk today is going to be about wildlife responses to climate change and carbon pricing policies, how that varies with different forest landowners here in the Northwest. So with that, John, welcome back. It's great to see you, and I really look forward to catching up on the sorts of things you're doing.
Yeah, thanks, John. And it is nice to be back. I wish I was in a big room in Anderson or some other campus building, but that's okay next time. Hopefully it'll be in person again. So I'll talk with some slides. I kind of have 3 parts. The first part is just in general, some of the ways that we, the scientific community, assess wildlife responses to the climate change. So some of that will be work that I participated in, but it's just more of a general background, a general look at how we assess those types of climate change effects. And then most of the talk will be focused on the specific paper, and I'll mention my co-authors when I get to that stage. And then at the very end, before I end the slideshow, I'm going to talk a little bit about the graduate program on the environment at Evergreen, just in case there ends up being undergraduate students or anyone else that wants to know more about it. So this question of how do we assess either current or recent or current effects of climate change? And then I'm sure a lot of you are aware of or may have done it yourself, the projecting or predicting what effects might be in the future. And this isn't going to be a comprehensive look at all the literature, but just some of the types of work that people have done. There has been quite a lot of actual observational evidence, empirical evidence that there are range shifts. And so this review paper found that especially in areas with greater levels of warming, you had range shifts towards the poles, either north in the northern hemisphere or south in the southern hemisphere. And to a lesser extent, but still measurable to higher elevations. So those are the directions of effects you would expect with warming. And just as an example, these were data for these 4 invertebrate taxa just in the United Kingdom. So this was a smaller data set that they presented in this paper. And it's, you'll see, other examples of this, including in our own work, where it's not that climate change affects all species equally. You see that even though most of the species, so all of the bars to the right side of this north-south divide, because we're in the UK, most species are moving the northern part of their range even further north, but there are some that move south. So whether it's spiders or ground beetles or butterflies or grasshoppers, more of the species tend to move north than they do south. Another area of observational data comes with phenological shifts. So phenology is, some people like to call it the science of the seasons. It's the timing of events. So whether it's the trees leafing out in spring, or birds coming back to their breeding grounds, or birds starting to breed, or frogs starting to breed, any of those seasonal events, people have, in a lot of places, have good records of when those occur. So this particular species, study looked at 73 bird species in Finland since 1975. And again, for across all of the species, these are, this top graph is expressed in terms of days per year if the start of breeding has shifted. And so you see that overall, the shift is slightly earlier, but it doesn't mean that some birds, and especially in some years, might not start breeding later. So again, it's not that there's a single effect, but on the whole, these types of shifts, whether it's start of breeding or the end of breeding, becoming earlier is what you would expect when there's warming, which means earlier springs. And then this is an earlier review paper, but Camille Parmesan has done quite a bit of work in the area of climate change, looked across not just animals, but herbs and grass, shrubs and trees, to see if there were changes in the timing, and these are across all different kinds of seasonal events, whether they were happening earlier, which you see the vast majority are below the line indicating earlier, whether they're later. But it is worth asking the question, so what? So, in some sense, if particularly more mobile animals, if they are shifting their ranges north, if they are coming back to breeding grounds or starting to breed earlier, maybe that represents an adaptation to climate change. Maybe that's what you would hope for. And that can be part of what's happening. It's not that this is necessarily bad news. But there's two major areas of concern. One is the pace of climate change, meaning what's happening year after year, and you hear about it in the press. It's another year that's the warmest year on record. This is a much faster pace than any climatic change in Earth's history that we know about. And so, just again, kind of out in the popular media, people talking about, well, the climate changes and animals have to adapt, or humans have to adapt. What is different about the current type of climatic changes is that pace. And so even if, yes, if some animals and plants are shifting ranges, but are they actually going to be able to keep up with the pace of climatic change? And then in terms of phenological shifts, what people worry about is what's called the resource match, or the problem is when there's a mismatch. So this paper had a nice schematic, and this is also work that, not this group of authors, but I've been involved with a group that's working on this, is so up here, this is kind of given current climate. You have birds laying eggs, and the adults need resources during that time. And then in particular, this is true of a lot of, especially forest songbirds, when the young are in the nest, they really rely on finding caterpillars, worms, invertebrates to feed those nestlings. And so the match is when the peak of the need of, particular populations that needs to feed their nestlings coincides with a peak in caterpillar abundance, then that's a good match. What's not on their schematic that I added was, of course, the caterpillars are eating the leaves, and so you need the trees and other vegetation to be leafing out. So studies, including the one I'm involved with, refer to this tritrophic match or mismatch, the three trophic levels of the birds, the insects, and the vegetation. So what people are worried about and starting to study is whether, because of some of these phenological shifts in the face of climate change, are you getting earlier green up and then potentially earlier a peak of caterpillar abundance? So that's if either the birds aren't shifting their breeding dates or they aren't shifting them enough, then the peak of the resource abundance is offset from the peak of the need of, in this case, the birds to feed their young. And so that kind of mismatch, it's interesting. It's a very complex type of phenomenon to study. And I would say so far there's kind of mixed evidence. It seems like in some systems this could be a problem. In others, it seems like, for example, if birds are arriving earlier, they're actually tracking changes in that resource peak of abundance. So it's something, this website is the group that I'm involved with. And maybe when we get more results, I'll come back to do another seminar on that. Okay, so that's certainly not everything that people have studied in terms of recent or current effects of climate change on animals or wildlife. The other kind of category I wanted to talk about in terms of some of the work going on are either the near term, short, and then also longer term, decades in the future, projected effects of climate change. So one kind of area that people have worked in, including Josh Lawler at UW, and some of these authors are former students of his, is to think about climate vulnerability. And that can be of individual species, it could be of habitats. And so this framework considers whether any given species is sensitive to climate change, meaning if climate change occurs, are they, what's their dispersal ability? Is their habitat going to be very sensitive to climatic changes? And then also considers the exposure. In the areas that that species is found, are those areas expected to undergo climate change? So that's one kind of area. And so Michael Case was a PhD student at UW with Josh. Of course, you have the bioclimatic envelope approach or species distribution modeling. These are ways that people, including Josh, have projected range shifts across many species to say, given the climatic conditions of where they're found in the current period, where are those going to be in the future? And I guess what's interesting to me about that, I mean, it is interesting to see the maps. And a couple years ago, another one of Josh's student, Chad Wesley, who's at Audubon now, was one of the leads on a big paper that came out with Audubon, and there was a lot of press about it, about where are certain species expected to disappear, where are they expected to show up. So those maps can be really interesting to look at, but you can also use those projected range shifts to ask, are species even going to be able to move into potentially suitable climatically suitable areas, given things like dispersal limitations? So Carrie Schlash was another one of Josh's students that did this for different groups of mammals. And you can see the expectation was, given what we know about those species within these different mammal groups, their ability to actually move, disperse, we would expect many more range contractions. Again, it doesn't mean that there aren't some animals that can keep up or that have better movement capabilities. So all these dots are individual species that might actually be able to expand their range. But the bulk of the individual species are below that 1-to-1 line. Of course, another approach, this was a more recent paper that I worked on with Josh and others, to think about, given where for dozens of different species, given the places that are expected to be more climatically suitable, if you consider those, can you identify areas that might be important that are outside of our existing protected areas network? So obviously this is the continental US, and this difference in importance refers to areas that are more important if you only consider where species are found currently, compared to the green places that show up are more important if you think about places that conserve species where they are and in the future. Not so much where they're going to move. That was part of a different part of this paper, but this single graph was considering that difference. And you can see, some of them are side by side, but there's quite a bit of difference. There's some areas that are kind of in this gray area where it's good for both types of places. So those are just some of the ways that you can use these species distribution models and thinking about conservation or what species might be particularly vulnerable. And then another way, this is not directly modeling what's going to happen with animals, but what's going to happen with their habitat. So a number of different groups, including Sarah Schaefer, who's at USGS, project vegetation changes. So not just individual, you can do these models with individual plant species, individual tree species, but this is wholesale vegetation, and they're mechanistic models that consider not just climate change effects, but the plant's differential ability to take up CO2 if there's increased levels in the atmosphere, and also climate change related disturbances like wildfire. And so this was some work of Sarah Schaefer and others that we used for a climate adaptation publication. So Julia Michalik led this effort. So this is Washington, Oregon, Idaho. The main thing to pay attention to here is the projection out, now that the 28ers are only 60 years away, of the replacement of the shrub steppe, which is this pinkish color, by either grasslands or grasslands and open forest and woodlands. And this was, with a certain set of global circulation models and a certain projection of emissions, whether or not this is exactly going to happen. The reason we use this term projection over absolute prediction is there's a lot of uncertainty involved, but we want to evaluate some of the changes that might happen. So you can imagine for all those shrub steppe dependent wildlife species, knowing that this might be in the cards is cause for concern. Okay, moving more specifically to the paper, this was a group that I got involved with. So Yukiko Ashida is the lead author. She was a PhD student of David Lewis at Oregon State. Yuki's at University of Georgia now. Dave Lewis is someone that I've collaborated with. I first met because of coming back to UW as a postdoc with Josh. Jeff Klein is a Forest Service research scientist, and then Tara Newman was a MES student. She didn't do this work as her thesis project. She did it on the side and was part of the wildlife component. So sometimes I like show pictures of the co-authors so people get a sense other than just the names. And really, these are just some images. I'm not going to try to explain the graphs until I get into it. But this was basically a different kind of way of evaluating how climate change might affect wildlife. So all of the things I just talked about, I guess, fundamentally we did use known habitat associations, but we weren't projecting species range shifts. We weren't using some mechanistic model of how vegetation is going to respond to climate change. It was something quite different. So let me talk about it. First, just as background, what this paper is focused on is private forest lands. So it's not the national parks, it's not protected areas, it's places where forest landowners make harvest and planting decisions that, they have to really consider the long term. If I plant, this plot with a certain species, what is it going to be in 50 years or 60 or 80 years when I might want to harvest it? And so in thinking about climatic changes that might affect what they want to plant, it can affect the timing of harvest. So maybe trees are growing better, it's more productive. Maybe other trees, because of local climatic changes, aren't growing better, aren't as productive. And then, of course, one thing that we and others are interested in is whether the decision to replant with a particular species is changing at all. And so part of what's built into this study is whether a particular kind of carbon price policy, so not something that's being implemented right now, but incentives for carbon sequestration, it's something that is implemented in other countries. And so red, reducing emissions from deforestation and forest degradation, that's a policy that has paid out money to people, and especially in tropical countries, to incentivize keeping forest lands forested. And so you can imagine that, part of this, the timing and intensity of harvest is about the timber prices. And if there's a carbon price policy that might affect the return of a private landowner of their of what's planted, that might influence their decision. So our research questions, what were the projected effects? So we are focused on, essentially, as you'll see, we're simulating changes to forests. And so we're thinking about, by the end of the century, what are effects of these forest landowner decisions on the forest types, the dominant trees that are being planted or replanted and replanted, and therefore on the forest dependent wildlife that are found in some of these areas. How do carbon price policies affect the trajectory of this change? And what wildlife species might be the most vulnerable to some of these projected changes? And again, it's not that we expect all of the changes to be bad for all species, but just like some of the other effects that you saw, there's kind of a dominant trend in the effect. That's part of the results that we got. So I'm going to talk about the data that was used in this econometric model. So the Forest Service FIA data, Forest Inventory and Analysis, has thousands of plots. We were only using plots on private forest lands because that's the scope. We're not trying to model decisions about public lands or public forests. The FI data is divided up a lot finer than this, but we ended up aggregating into these 6 types. So we're the plots dominated by Douglas fir, by fir and spruce, by hemlock and Sitka spruce, by ponderosa pine, other coniferous trees, or hardwood. And I guess I'll just say now while I'm thinking of it, hardwood deciduous trees covers a lot of different species. It is kind of one limitation, is everything's lumped into the single category. Really, Dave and Yuki did this part where they could use all of the FI plot data from this almost 15-year period and associated observed harvest and replanting decisions with biophysical variables such as soil quality, with the climatic variables at the time, and with timber prices at the time. And so they essentially built the model on this observational data over this time period. And then they used the model to project what would happen through 2090, either what's often called a baseline or business as usual scenario. So for this whole study area of the 3 Pacific states on private forests, given these observed changes, what is expected to happen in the absence of climate change, given changes to timber prices and what's known about forest productivity. Oops, sorry, here we go. And then a second scenario with climate change associated with it. And I'll talk in a little bit more detail about what we used for the climate change model. And then a climate change with carbon pricing scenario. So the climate change only used this RCP 8.5 projection, which is from NCAR. And so this is a fairly, well, it itself is a business as usual, meaning the world is not reducing emissions in any significant way, which unfortunately we're more on track for something like that than any of these climate change adaptation or mitigation scenarios. So that's the climate change scenario that we used. And you see under that scenario, there's a lot of, these are just categories of change from much drier and much warmer to wetter and much warmer. You see there's not any category of colder, which just reflects the reality of looking out to the end of the century. But there are significant areas across the study area that are wetter. And then others that are either drier to much drier through kind of most of the interior, including South Puget Sound. Okay, so that's the climate change scenario. And then the climate change plus carbon pricing includes direct payments to landowners for carbon sequestration. So how much is sequestered, meaning how much is the plant taking up that stores? I believe it was all above ground. And so there's calculations involved for a given species. Here's how much you would expect carbon you would expect to sequester it, with increasing amounts of payments going out over the decades. And this includes, so that's the incentive to keep plants, in this case trees, growing on your land. It does, the carbon price scenario includes a tax on the carbon released if it's harvested. So it doesn't mean that you can't harvest it, it's just that there's somewhat of a disincentive to harvest it. Okay. So first, this, I haven't really gotten to the wildlife section yet. This is just focused on the the different scenarios. So first the climate change only scenario, and then the climate change plus carbon pricing scenario, relative to the baseline, relative to the business as usual scenario. So these are relative changes, not just the absolute, is there more or less of a particular forest type. And because Douglas fir, especially in this part of the 3-state area, is such an important, so important to private forest owners, it was also subject to the most amount of change. We could do this for each of the forest types, but we're highlighting 2 of the groups. One, the Douglas fir. So you see all these, this geographic division as an ecoregion. All of these areas in red are subject to 10 to 16% loss of Douglas fir plots relative to the baseline. And the main difference between, you'll see this kind of repeated through different results. The main difference in looking at climate change with carbon pricing is a difference of degree. It's not that the direction of the changes are that different, but the ecoregions that have the highest amount of, I guess, loss of Douglas fir planting relative to the baseline, it goes from 10 to 25% change as opposed to just 16. And then you see, some of these are changing categories from a lighter to a somewhat darker shade of red. So if there's less Douglas fir being planted, what's the replacement, so to speak? Well, overall, it tends to be hardwoods. And this is true both in the climate change only scenario and in the climate change plus carbon pricing. Again, you see in that highest category. So this is more hardwoods being planted relative to the baseline by ecoregion. Okay, so now we can focus on wildlife, and this is really kind of where I was asked to participate in it, and I asked Tara to help with some of the calculations. We decided to use these state lists of species of concern. So these aren't necessarily, they're certainly not all endangered, federally listed species, but we wanted to use this as an indication that these are some of the species that the states are looking out for from the beginning. So we had to then filter those lists to say, well, are they associated with forest habitats in the first place? Are they associated with only some forest types? Because if they're just a forest generalist, it doesn't really matter if the forest type is changing, they're gonna have habitat. We wanted them to have enough of a range that they overlapped. We just picked at least 500 of the FIA plots because that's the basis of projecting the changes in habitat. And also that it wasn't a old growth specialist. Again, because we're focused on private lands, they're undergoing harvest. So those old growth specialists need to be protected some other way, or the habitat needs to be provided some other way. So as an example, this bird species, oak titmouse, we have the species range. It overlaps some of our state area. The Southern California extent isn't in there. It's associated with pines, other coniferous and hardwood habitat types. So for every species, and I'll show you all of the species after this slide, using the current range, we asked how much potential suitable forest types were there under the baseline and then under the climate change and climate change plus carbon price scenarios. So based on this, both the specific geographic range of a species and the specific habitat associations. And then we calculated the relative gain or loss. So a species could end up gaining habitat under these scenarios, and it could end up losing. Because of the way the simulations worked, we were able to do a path over time. So those amounts either gained or lost were calculated at 10-year time steps. Because there were included in the simulations was some stochasticity, some randomness. And so we ended up with, I can't remember if it was 1,000 or more simulations. And just as an indication of uncertainty, we used the tails, which we defined as the top or bottom 5% in terms of how much change there was in the forest types, to create prediction intervals around. We use the median amount gained or lost for a given species. So even though the plots I'll show you for the species just show a line for each species, there is uncertainty, or really a prediction interval associated with that we could use to say whether that amount of gain or loss was significantly different than 0. Okay, so some of the species that made our study were amphibians. I think we had 8 total, 12 or so birds, but also, different groups of birds, and 15 or so mammals, most of them small mammals, but some of the larger carnivores. And some of these were ubiquitous throughout the region. Some of them are fairly specialized. So, we wanted them to have a certain size range, but especially some of the salamanders have a fairly limited range. Okay, so here are the species-specific trajectories. So this is gain if it's positive on the y-axis, or loss if it's negative on the y-axis, of what we considered suitable forest types within a species range relative to the baseline scenario. So this is just the climate change scenario. And some of the individual species are named, not all of them, because then it would get too messy. But I'll walk you through this a little bit. So out of the 35, 4 of the species had a significantly positive amount of forest, of suitable forest types under the climate change scenario. And 2 of those, the pallid bat and ringtail, greater than 5%. Now this, keep in mind, this is out to 2090. So 70 years from now, a 5% increase isn't a huge increase, kind of marginally over that whole time period. But, it's the results we have, so we're gonna look at them and think about them. 5 of the species, those are actually the ones that are grayed out, had non-significant changes, meaning even if the median change was down here, the prediction interval with that method I mentioned before overlaps 0. So we're not considering that a significant change. But then 26 species lost habitat under this scenario relative to the baseline. A lot of them, fairly close to 0, but others, including these 5, lost between 10 and 20% of potential. Not even losing it. They had 10 to 20% less suitable habitat compared to the baseline. So that's just under climate change. Some of you might know something about these species. Not surprisingly, given the results that I talked about in terms of the dominant tree types, these winners tended to be species that specialized either on pines and or hardwood habitats, so able to use kind of that range of forest types. And the greatest losses were those that specialized in conifers, including Douglas fir, spruce fir, and not including pine. So I didn't show you results for for ponderosa pine dominated, but of the conifers, that's the one kind of type that we expect to have more of in this study area. Okay, so with the carbon pricing policy, I'm going to go back one and then come back to this. So notice the y-axis on this plot is the maximum or the minimum value is minus 25%. On this one now it's down to minus 35%. So it's not that everything's shifted down, which makes sense. So those are the same two species that are kind of winners, but now they gain even more, 10 to 15% in habitat. And then at the lower end, now we have 8 species that lose between 15 and 35%, or have 15 to 35% less suitable forest types compared to the baseline. So similar results, it's just that the magnitude of the effect is greater for some of these species. And I am getting close. Oh yeah, and then the median loss across all the species, or the median result was a loss of 4.1% compared to, under just climate change, the median was a loss of 2.1%. So again, it's not changing the direction, but it is exacerbating some of the potential losses. So these were some of the questions we wanted to try to ask. And I'll say how we decided we answered them. What are the projected effects of forest landowner decisions on wildlife species of concern? On average, more species had losses compared to gains in projected suitable forest types. Carbon price policies affected the trajectory by exacerbating that loss for most species. Again, for those 2 species that gained, their gain was higher. And then the wildlife species and forest types that are the most vulnerable to projected changes, the Douglas fir forest type was reduced the most, and so those more vulnerable species are the ones that specialize in some of the coniferous forest types, but not the pines and not the hardwoods. So, there's a fair number of mitigating factors, and it's certainly not that we're saying we shouldn't do a carbon pricing policy. So number one, we're not modeling species range shifts. So it's possible that part of what a species could do is move into places where it's not found today. And just because a species has certain forest type associations now, it doesn't mean they couldn't adapt to different or changing forest types. Especially looking out towards the end of the century, the magnitude of change for most species isn't that large. And it's important to remember, none of this study considered habitat on public lands or protected areas. But we did see how much of for all of these species, how much of their range overlapped currently protected areas, and the median across those 35 species was only 16%. So it's not as though most of these have huge parts of their range that are already protected. And so I think that kind of the overall finding I would emphasize is a carbon pricing policy is essentially incentivizing a single ecosystem service. So of all the ecosystem services that forests can and do provide, this type of carbon price is basically incentivizing carbon sequestration. And that's just one of the many services that forests can provide. So we're just kind of saying, well, it's useful, it doesn't mean we shouldn't do this, but we have to think about unintended consequences, including on some of these wildlife species. And all of the recommendations that people have been trying to think about and trying to promote that could support any of these species' ability to adapt to or respond to climate change still apply. Particularly, so it's not that we necessarily need to do something different, but thinking about habitat connectivity, thinking about removing barriers to movement, thinking about potential climate refugia that aren't expected to change as much, even with some of the projected climate changes, are going to be maybe even more important for some of these species. Okay, so that's my reminder, and I'll be happy to answer questions about the talk, but I did want to just say a little bit about the graduate program in the environment at Evergreen. So there's actually 3 graduate programs at Evergreen. MES, the one that I teach and work in, the Master of Public Administration and the Master in Teaching. And so anyone that might be graduating this year or might be thinking about it next year, we are accepting applications for fall 2021 this fall, and I'm sure, like the UW, we're hoping that we'll be back in person by then. And in some ways, John in his introduction mentioned the urban ecology program, which was explicitly interdisciplinary, and we did research in graduate student collaborations. And that experience really helped me speak intelligently when I was interviewing for this job about interdisciplinarity, and it is part of all of our courses, not necessarily all of the MES theses. It's not as though for a master's thesis you have to do something that's interdisciplinary, but we do have faculty, I would consider myself more with a background in the natural sciences. We have environmental sociologists, we have people focused on energy policy or other policies. Most students either are in the program full-time and finish in 2 years, or people that work full-time are on the 3-year track, so they don't take as many courses in a given quarter. But because all of our courses are in the evening, it's designed for the ability for working professionals to do the program. They can still finish with a master's in 3 years. And the one main difference one of the main differences between the MES and what I would think of as a more traditional Master of Science program is that you start in the fall with a cohort of other students and you go through and take required courses. And then after that first year is when you get a thesis advisor assigned. So a lot of MS programs, you would need to identify, which of these professors is going to be my advisor, and you don't have to do that. It's part of a process that we go through after students have been there a year. So I think that's all I wanted to say about MES, and I'd be glad to answer questions. Thanks very much.
Awesome. Thanks, John. We can clap silently for you.
Thanks. Yeah, I know the Zoom environment. So I'm going to pull up, I do see Rebecca's question. So yes, marbled murrelets are definitely considered an old growth specialist. They need the large trees with the big branches and platforms. And so that, they're a seabird, I'm sure most of you know, they're coming in to nest on these big platforms, trying to avoid the jays and crows and ravens, right, John? Yeah, but they need the big trees. That is not going to typically be found in a rotation forestry type of environment.
If you guys have questions, you can post them in the question and answer or the chat, or raise your hand and we can call on you, I think, although I can't see anybody.
Thanks, Sergey. Yeah, I think if we open participants, if you do the raise hand feature in participants, we can try to call on people too. But I guess you'd have to still type it in.
See that question from Dan?
does the equilibrium nature of the models limit our ability to look at impacts? Yeah, I mean, I think, so I'll answer that generally, which is, I guess, and you could think of it as, you're asking a question about limiting our ability to look at impacts. These simulations are limited to the types of changes that were observed in this single, 14-year period. So, and, I definitely have the sense with any of the projection work, I've been involved with. I think it's worthwhile. Otherwise, I wouldn't do it. But, we don't really know what the environment is going to be like, what global timber markets are going to be like. That, in the sense of, we don't have a reliable way of predicting what's the actual environment is going to be like in 70 years. I mean, some people would probably disagree with that, but the purpose isn't so much saying, oh, this is the future that we're going to be in. The purpose is more, with these relative changes of, the climate change or climate change with carbon pricing relative to baseline, this type of policy might influence the trajectory in one way or another. Not that we have the right path necessarily, but it does, the fact, in some ways, the fact that it's empirically based, the model itself, is a strength, because we can say, well, these are not changes that go outside of the bounds of those that have been observed, but it's also a limitation because of that same fact. It's not going to suppose some dramatic change in how how timber comes to market or how landowners are making those decisions. Yeah, there are Sergey's point about considering potential changes in global markets is true. Yeah, that kind of the pace of change is definitely a concern. Yeah, I didn't say, one of the recommendations that people have talked about is assisted migration or translocations for those, not just animals, but, tree species that might not be able to keep up with that. And that is, it makes, I think it's worth putting everything on the table, basically. The sort of tension between what I would call the more traditional conservation, let's protect land and limit activities on there, and here's our boundary. There's a lot of thought and effort to get away from that, and it doesn't mean that we can't still do that. In some ways, that tension has been proposed as a either or, but it doesn't mean that protectives aren't important. It just means that the basic approach of let's find whether it's the most biodiversity or the most threatened biodiversity and kind of lock up that land doesn't really address the needs of that pathway. How are species moving through the landscape? And so that's where thinking about connectivity, thinking about the working landscape, which certainly private forest lands are. The one, I remember a graphic you showed, John, that I've still used in my classes of, what's the level of change of a clear cut compared to a parking lot, and the ability of the land to, of forest to grow back is a lot more limited when you have pavement, put it that way. The biggest barrier to wildlife moving their ranges, just to continue, it's one of the biggest barriers is the lack of habitat connectivity, meaning there might be a climatically suitable place and it might be relatively undisturbed by humans, you know, if that's kind of what the species needs. But if there's no way for that species to disperse to that area, because, you know, to get to that new area, you have to cross highly developed areas or lots of roads or, you know, other limitations, that is a big issue. And so some of the connectivity work, I mean, there's a Washington Habitat Connectivity Working Group. I think I missed a W in there. They have a really long acronym that has included Josh and people in his lab and people like Mead Crosby, who's at UW too, is, you know, thinking about that for Washington, about that very question.
I have one question for you, John, just to make sure I'm seeing this right, but the accentuating effect of the carbon pricing is because the land managers are anticipating the change in habitat quality and going away from Doug fir? And are you assuming that kind of through the independent choice of landowners or just modeling it?
It's modeling it into the future based on observed decisions of that 2001 to 2014. So whether that, I mean, and I haven't dug down into the weeds of those, but whether it's because of climatic changes over those periods, or saying, well, if you incentivize because of the carbon price, you know, if they know that they're going to get a bigger return by planting a different species and holding it in that species for longer, that would be part of the simulation.
Yeah, that's what I was wondering. That seems, it'd be interesting if that's the, you know, to talk with some of those landowners and see, are they thinking about that? Would they change their planting based upon that incentive?
Yeah, and that's sort of like, because it's not just you know, it's not just what I think is going to give me the biggest return. You know, that's sort of the rational, the myth of the rational actor. It's, you know, what I'm comfortable with, what my tradition is of this land. So I think, you know, some of that, it again, like these changes are based on observed changes, but I think there's also going to be a factor of kind of the stickiness of, well, this is what we've done, or this is how we've managed the land, and we're not, you know,
always done it this way.
Yeah, exactly.
All right. Well, I think we'll stop the questioning, but there is opportunity for any grad students or others if you want to hang on and ask more questions and talk with John. He's glad to do that. Maybe he can drink a virtual beer. I don't know if that's been possible before, but I mean, we ought to be able to figure out a way to do that. And again, I would thank you, John, for your time and sharing your expertise with us today, and for everybody for coming and listening.
Yeah, glad to be here. Thanks, John.